Since last time we talked about installing Visual Studio and setting up your environment, I'm just gonna use my actual environment now. Ooh, sorry, I think I hit the microphone. And we're just gonna jump straight in with this little idea I have. Last time I saw, I've showed you this method, read key, which blocks the program, which just freezes everything until we hit any button while in the console. Let's just quickly try that. And I believe you won't be able to see the... can I... Wait, let me see if I can... Nah, you know what? Never mind. You didn't see it, but I just pressed a button in the console and then the program continued. Actually, maybe I can add it. Let's see. Can I quickly add a new... Does OBS automatically add that? Let's see, window capture. It's the console. That one should be it. Then maybe let's put that into the center here. Okay, so I'm just waiting for key press, and if I press it, program ends. It's gone. Does it automatically reappear? Yes, it does. Cool. Okay, so we're gonna leave that. So that's the read key, and I've mentioned that we do actually get return value. And that return value, I'm just gonna quickly store that, is the key info, which is just the information what key we pressed with a bit of extra. So if we look at the different options, which we can do inside of the IDE by just using IntelliSense, you can see we have 3 different properties here. This is the one we're gonna use later, just quite convenient. It's just basically the character encoded as Unicode, UTF-16 in case of C#. We talked about that a couple of lessons back. We have the actual key, which is an enum. We learned about those last time. And here we have all the different types of keys you might press. And we have a modifier, which is another enum, which is just, did I press the button on its own, or did I press any combinations of other buttons? And now I just want to capture a few key presses in the console and then print out the entire sequence that I typed in. Basically, I want to be able to type in a text, but I want to code that myself instead of relying on external libraries. Right? So the idea is, let's just start with a rough outline. True. God, I missed this. All the little shortcuts, all the little helpful, I'm adding stuff for you, and indentation, and it's good to be back in an actual dev environment. True. Console.read key. Just name it like that. And we need to store this now somewhere. Like right now, this is just gonna run endlessly, while true is an endless loop. Because this condition is always true, because it's literally true, and we never have any abort. We have no return that would end the entire method main. We also don't have a break that would just abandon the loop. Nothing happens. This would run forever. It's just pausing in between to read a key and doing nothing with it. So how do we store this? When I run the program, I don't know how many key presses I'm gonna do. Right now this would run forever, so I have to store an infinite number of keys. That wouldn't be too great. So we should probably add a condition to abort at some point to limit the amount of keys we record. And for that I'm just gonna make simple if press key is escape, break. Alright, so we press the key to continue the program. If we press the escape key, program stops the loop and we can do something after the loop. If it's not escape, we can capture the key information somewhere. But where do we do that? Since we still don't know how many key presses I'm gonna hit, we cannot rely on a static storage like a normal array. If I have an array, so info, press tease, so like that. If I do this, then I can only store 10 keys. I could maybe go for a really big number, a number that I probably won't hit, but I can't be too sure. And if I do not hit this target, then I've wasted a lot of space. So a static storage doesn't really work for our situation right now. Well, we did discuss an alternative way to store data before we introduced arrays. I could make a class storage, for example, that stores a console key info value. Let's make it public. So just a normal field. And that stores another instance of storage. Pay attention, this is a class, not a struct, that's important. We wouldn't be able to do this if it was a struct, because then we would store an infinitely large object basically, because the entire space a storage needs is contained in just the next, and then we add some additional info. But that means storage itself would get bigger, and yeah, that doesn't work. We have a class though, so this is not actually the full memory we need for a storage, and just a pointer, an address in the heap where we can find the next storage. So it's always storage object contains a specific key and an address where we can find the next key. And what we can do now with that, storage first equals new storage. And then we're gonna say storage current first. If it's escape, we just stop. And we're gonna just say current dot value equals press key. Then current dot next equals new storage. And current equals current next. And now I could just go to first, read the value, then first dot next, read the value, and so on. This is a linked list, basically. Not the prettiest implementation, but in theory it works. In every loop, we just add a value to the current item in our linked list, then we create a new item that we link to, and we remember that new item we just created, that new last element in our list, for the next iteration of our loop, so we can put the next value in that new item. And in the end, we can use first to start iterating through the list and read through all the individual values in there. That works. But linked lists are... well, actually, they are a pretty good solution. But they all have their little inefficiencies. Mostly I have to slowly iterate through all the different values. And I waste a lot of space. I have this one console key info and a pointer to the next element, and that for every single key press. So I have a full instance of an object for every single key press I do. And a key press itself doesn't really take all that much space, so it actually does take more than a pointer, admittedly, but still. In terms of memory, not the most efficient, and linked lists aren't always the most comfortable to work with if you have a large number of items that you just want to work with. We don't have an easy access to each individual value. So arrays are still the better in that case. But linked lists offer us the ability to dynamically grow how much memory we use. if we were to try to use arrays, how could that work? Well, let's go back to that. Console key info, make that an array. Press keys. And console info, and let's just start with an array of 0 length. By the way, the green squiggly lines in here are because there's a better way to handle this, which is more efficient, so can just do this. I'm using .NET 9 right now. That means I'm also working with the newest language version. I think we're at 13 right now, C# 13. And this is one of the newer features we get. But it's still the same old. I'm just creating an array with 0 elements. So how would that help us? Well, we could also go for 10 elements. Same story actually. If I were to add an element to our array, well, first I need some indicator of where to put it. So let's add integer count 0. That lets us know how many items we've already added, so we know where in our array we should add the next one. And that means here we can just use press key count plus plus equals press key. Press keys. Okay, let's rename this infos like that. Another advantage of IDEs, it can just quickly rename this and it really rename it everywhere where I use that variable. It's a bit more reliable than just search replace. So now I iterate through the array, so to speak. In our first loop, we added to index 0, and we also increased the counter from 0 after we used the value 0 to 1. And so on the next loop, in the second loop, we have infos at index 1, set to press key. Third loop, infos index 2, set to press key, and so on. But now we get an exception when we hit our 11th key press. To go around this, we would need to increase the size of our array. And that's why it doesn't really matter that we have 10 elements in the start. We can also start with just 0, because we have to add the logic to increase the size for our array anyway. And how do you do that? Well, let's write a simple method. We can check if count, if the number of elements we've already stored is greater or equal to the number of elements we can store, the total length of our array, then we have to increase the size. If the total count of items we've stored is less than the current length of our array, then we're fine and we can just add it. So how do we increase the size of our array? In short, we can't. There's no way to increase the size of an array. It's fixed in length once you create it. What we can do is create a new array that is slightly larger than the old one and copy all the values to the new array. So we can do console key info new array equals new key info, and we use the old info.length plus 1. So the new array will be exactly 1 item larger than the last one. In our first iteration, that means we start with an array with exactly length 1. And now we use a simple for loop, less than length plus I, and for each, yeah, okay, you can already see IntelliSense is pretty quick to understand what I'm going for. You see it gray version of the code that it suggests I'm adding in, and you can just hit a tab and it's adding it. It's indeed the code I want. I want to add at each index that is available in the old array infos. I want to take each of those indices and copy the value at infos at that indice into the new array. Just a simple copy operation. All the data in infos gets copied to the exact same location in new array, except for the very last location in new array, which is now free to be used for whatever key press I have here. So this code, let's actually use the new logic here, will create a new array that's exactly like the old one with just one extra free spot in the end. So we can just reassign the variable infos to point to the array we created here. Keep in mind, infos equals new array does not mean we copy the data. To copy the data, we have to go through each index individually. What we did here is simply assign the address for the new array to the variable that stores so far the old array. We have an array. Arrays are classes, instances basically. They're stored on the heap. That's what I'm getting at. And so this is just an address to a part of the heap where a lot of data might be stored, depending on the size of the array. So with this structure, we can use an array and still have a dynamically determined number of items. We do not know how many items there are going to be in the array in the end. It doesn't matter. However many items I pressed, that's how many spaces I have in the array in the end after the loop is done. So let's test that out for each. Actually, I'm gonna laser for each things I can do in an IDE. And console.writeLine, and we're gonna be very lazy and just go for, is it console key info, keychar. Just gonna print out every single character we've added as a single line. And in theory, this should work. Let's try that out. These are the characters I typed in. I did not activate the intercept, so you can see exactly which buttons I pressed. Now I'm hitting escape. And we're getting hello. Didn't print out the H. What did I miss? Honestly, I'm kind of confused right now. There must be something obvious. Why did it not store? I mean, in principle it worked, but still, well, that's why we have the debugger. Let's just use that as an exercise and step through it. Let me hide the console window so we can step through here. So we have first the read key. Let me press a button. I pressed the button A, by the way, so press key. We look in the IDE now. Press the button A without any modifiers. And count is 0 because we're in the first iteration. Our current array has length of 0, so we hit the if branch, that's correct. We create a new array that is now a length of exactly 1. We copy all the values over. There are no values, so this loop ends immediately, and infos is now our new array. And we store at index 0 in our old array value A. So that works. Press next key. I'm hitting escape. Hitting break. So infos is just filled with our A. we're done. And if we look at the console again, that's what we get. Is a read key maybe not respecting the... Okay, let's try that. Just add a new line before outputting stuff. Might learn something new today as well. Hello? Hello? What am I missing? I'm missing something. I don't know what. Info contains H E L L O. Adding new line. And then press H. Its output is there. I'm confused right now. Honestly, I don't get it. I know I'm missing something. I don't know what I'm missing. Why is it not... I'm really confused. Let's try... It's not outputting the H. Or am I just not... Am I blind? Am I just blind? Is that it? It's not outputting the first one. Okay. Let's put that back in still. Does that have an issue with the... Nope. Okay, you know what? I'm just gonna ignore that for now. Because I bet when I look at the VOD, when I make the description for that, I'm gonna see immediately what the issue was, and I'm gonna be so pissed. But we're just gonna ignore it. We're just gonna pretend that everything worked exactly as it was supposed to work in my head. We continue here. Writing this code doesn't take much space, doesn't take much time, but it's a bit meh. Do I really need to write this out? And the answer is of course no. Especially when you have to write this out several times in a larger program, you would definitely put that in its own method. So we can make that public static void resize. Let's do it like that. And let's also make that a generic method, because we learned about those. And we're gonna give it an array t, right? And we're gonna give it an integer to tell us how much we should increase it. And let me just... Never mind. We make a new array for tease. New t, and the size is gonna be array.length plus increase d equals 0, I less than array.length plus I, and then new array I is gonna be array I. Now here we can do two things. We could either decide to just return the new array, in which case we would have to do this like that, or we could go the other way and just make this a ref and then set this up. If you remember the ref keyword, what that would mean is we can do this away, and then just resize ref infos by 1. Like so. Let's remove the brackets. And this code would work. So ref is something that can be easily exploited in wrong ways. Let's switch to the more obvious what it does, but a bit more work to write out version like this. Still does the same thing. Copy the values over to a new array that's a bit larger than the old one. And this time we actually have a variable. Instead of fixed increments of 1, we increment by how much we need. Because I can actually increase by 10, for example, instead of just 1. Now the question, why would I do that? I'm only adding one more item. Why would I bother adding more than one item to the array length? In the end, if I don't use that space up, I just wasted a lot of memory, right? True. But on the other hand, if I increase the length only by 1, that means in every loop iteration, I'm gonna create a new array that's gonna use up more space than the current array are already blocking in memory. So I have to reserve more space than I already use, copy over all the values, which takes time, and then in each loop iteration, this process gets more intensive and heavier because we need to reserve more and more space each time. We need to copy more and more values each time. And even if the garbage collection works super efficiently and immediately clears the old memory once we don't use it anymore after this line, so the old array gets freed up in memory, even if that happens, the garbage collection will add a lot of extra performance. And if it doesn't perform perfectly, the old array will remain, and we have the old array, the new array, and the new array in the next loop iteration, all blocking memory, until garbage collection has finally time to catch up and clear all that out. If instead we reserve 10 items, that means for 10 iterations of the loop, we don't have to do this. We don't have to reserve new memory, and we don't have to copy all the values. That means we have to reserve a bit more memory in one go, true, and we might have wasted that extra memory, because we reserved more space than we actually needed. But that's a trade-off you will have to do a lot when you start programming. Because there is sometimes an ideal solution that exactly solves your problem in the most perfect, most elegant way. Those situations are rare. You will usually have to make a trade-off. You have to find optimal strategy for your specific program. You cannot always assume this is a solution that fits everyone. Depending on your situation, just adding one might actually be perfectly fine. That is if maybe you just have 2 or 3 items. But in those cases, if we're just talking about 2 or 3 items at all, maybe just make an array with 3 spaces to begin. And just accept that maybe there are 2 spaces not used. If we're talking about a situation where I potentially press a couple hundred button presses, well, adding 1 is wasteful. Adding 100 might actually be more what I need. In the end, 100 extra items in the array isn't actually that much space. If you were to try to calculate how much memory does this actually use, well, what does the console key info actually store? Let's have a quick look here. We have the key char, and the modifiers. And I would assume that the Unicode character is actually a calculated value. I would have to check the source code though. These are properties, not fields, so we do not actually know if it's a value that's stored directly in the struct, or if it's calculated through a method when you read that property. let's assume that we only have the two structs for the actual key pressed and the modifiers, and the character is, or the Unicode character is processed from that. In that case, we have two enums, which I assume are just standard int enums. I'm running as, int 32s, two int 32s, 64-bit in total. So just 8 bytes. And 100 items means 800 bytes. That's not even a kilobyte. If we look at it that way, 100 items that we do not use, or maybe 99 items that we don't use, sounds like a lot, but then it's not even a kilobyte in memory. Nowadays, that's nothing. Like a kilobyte, sure, put it there. If it helps performance, that's worthwhile trade-off. Copying this stuff over is much more costly, and having the garbage collection do extra work. So how do you find the optimal strategy for how many items should you reserve each time? Again, it's not that there's one optimal solution that fits everybody. That's why if you write this code on your own, you have the option to define everything exactly how it should work for your specific code. However, if you have to write a very general library, one that can fit many, many different people, you will have to settle for a solution that works pretty good in most circumstances, but will probably also be very much terrible in very specific scenarios. And one strategy you can do for a general case when you're not too sure about the actual performance usage and how it will turn out is, instead of increasing it to a fixed size, increase it to a size relative to the existing array. If our initial array has maybe just 5 items, adding 100 is a bit overkill. But if you have already 1,000,000 items, just adding 100 seems a bit too little. The common strategy would be to just take the old length, add it on top. You double the length of the previous array. Well, that's why I increase it by the same length again. That means if I start with 1 item, now I have 2. If I have 2 items in my old array, now I have 4. So the more items I add to the array, the more I will increase its size later on. The bigger the array gets, the more likely it is that we're gonna add a lot more items, right? A very big array is probably gonna take in a lot more additional items than a very small array. At least that's what this bangs on. The larger the array gets, the more the performance cost will matter for reserving extra space and copying the stuff over. And to compensate for that, we will decrease the frequency at which we have to run this entire code. We're just making it less and less likely by reserving just more space each time we have. Does that make some sense? Yeah, maybe. And yeah, doubling it up is very common. That leaves us in our situation here with a very specific issue. In our first array there are 0 items, and 0 plus 0 is still 0, so that wouldn't work. We could just go for a minimum. Just say if the increase is less than 1, increase. If increase is less than 1, just set increase to 1. And in that case, we capture that case. If we increase the array with a length of 0 by 0, we actually increase it to at least 1. And the next time we would increase it by 1 for real, to a size of 2. And third time would increase it to a length of 4, and then to 8, 16 powers of 2. Of course, we could also just start with an array that has a certain number of elements. console key info, like that. Again with the 10. That means we start with 10 elements, and if we do not have enough space, we increase it to 20 and go to 40. Not quite powers of 2 anymore, but it's still the doubling up. So that logic still remains the same. Let's just test it out. Does it work now? That was an enter. It seems to be the output again, except for the first character. I still don't know why. And I'm not gonna look that up. So this works quite nicely. But I have to still write this out myself. And I also have to keep track of the total amount with an extra integer variable in my code here. Wouldn't it be great if I can just have this be gone and get that away and get this away and just have a simple array on the top and just add the value to our array and be done? Just make it a bit simpler to use. Oh. That's what we're talking about today. We're gonna make a specific class. Make array, let's just call it like that. And this dynamic array will have internally private... Actually, let's make it generic as well. Can store anything. It will store an array with values. And it will store integer with our count. How many items do we have? The same as before. And yeah, let's write a constructor really quick. So we actually do have something. Yeah, let's do it like that. We're gonna start out with an empty array. So if we don't actually use the array, if we never add anything to it, we also haven't reserved any space. Keep in mind, an empty array with 0 elements is still different from having null. So even if the array has length 0, it is still occupying some space on the heap. This array will still point to something on the heap. It's just that it's such a minuscule amount that you might as well neglect it totally. Also, because it's not using any elements, you could use the exact same address for other arrays with length 0. Since you cannot change anything about it, it doesn't matter if different parts of your program reuse the same address to an empty array. So yeah, do it like that. And now we need a way to add something to the array. Public void insert. That's the classic name for a method. We're just going to give it an integer index and a value. And it's just going to array index equals value. Right? So that's a replacement for this line basically. Let's replace it as a whole. So dynamic array console key info infos equals new dynamic array. And also a new feature, I can just write this. Because we're on the same line, the compiler knows that we're talking about a dynamic array. For console key infos, I don't need to specifically write that out here anymore. And in here, instead of doing that, I could go for infos.insert. Like that. This would be the counterpart to earlier. But that means I still have to count myself. And we already have a count here. So instead of doing that, we can... nope. In this case, the IntelliSense did not guess right. We make an add and just t value. We just want a method that receives the value and automatically adds it at the end of our list. the array. Yeah, we'll deal with that code later. Add to value, and then we're just gonna go for array count plus equals value. Right, the same code we used earlier, just inside a method now. We could also go for insert count plus and value. Just call the other method. So our insert method is the only one that actually adds something to the array, and the add method just reuses that method. So if there's anything we want to do specifically when inserting data, we only have to change it in here and not in the insert and the add method. Right? Now we have to do the resizing, and we can actually do that internally, so we don't need to expose this method. And let me just quickly turn on the lights, and here it's getting dark. Just a second. Also have to shut the windows. That's better. The warmer season arrives, but the sun is still out pretty early. Alright, private void resize, and we don't even need any values in this case, because what just happened? Because we have everything at our disposal already. So we know we have the old length, and we want to increase the size by itself, we not double it up. So we just make a new array. Not quite count, but instead we go for array.length plus array.length, like this. So we just double the array length in total. I'm not doubling up the count, which in theory you might think that count is already array length, because otherwise we wouldn't hit resize, right? But that might not be necessarily the case. So we're focusing explicitly on the length of the array. So we're doing this. And because we want to be sure that it will increase the length to something, do this, and if the array length less than 1, just a very primitive, straightforward, setting it to 1. Right? Could also do it a different way. We can potentially optimize a few things. This one is 1, and else like this. Or if we want to be clever like this, though as far as I know, the performance is actually better with a multiplication in this case. Right, int array length, like that. And we can put this in a trinary, like that. And in which case we actually don't need the value anymore, and we can also do this. A lot of fun stuff we can do. I just like to play around with the features. I miss them so much. I don't really get to use that in recreational use. I'm used to doing that for work, but this is a very different context. It feels different. It feels like a toy right now. Weird. Anyway. We have an integer I that we're gonna start out as 0, and we're gonna iterate again through the entire old array. And we increase the size to double that of the old one. That's okay. So we just new array I equals array I. Whoop. And then we're gonna say array equals new array. like that. And so we have a method resize that will resize everything. And what we can do here is we check if count is greater or equal to array length, resize. So if the count hits the threshold, we call the resize method, which will do everything in here. Create a new array with double the size of the original, but at least a size of 1. Copy over all the data from the old into the new in the exact same indices, and then use that new array and forget about the old one. And if the count was less than that, or the resize method finished, we could just add it at the next count. So we just add the value using the insert method and everything is done. So this should work without crashing. Let's give it a try. Actually, yeah, you can see it. Perfect. A, B, C, D. Escape. No crashes, so that worked. Of course, we didn't really see anything, so let's try that with a breakpoint here. A, B, C. Okay, A, B, D, C. With an enter in the end. Let's have a look at infos, which has internally the array, and that's going to be A, B, D, C, and return 0, 0, 0. Now here's the big question: what are these zeros? Why are they here? 3, 2, 1. They are the reserved space we had earlier. Because we doubled up the array, but didn't use all of that, we have some free spaces in the array here that are not used in any way. And because console keyInfo is actually a struct, not a class, those empty items are not null, they're filled with a default console keyInfo, and the default value is just 0. So that worked. We now have a convenient little array that we can just add items into. Now let's also make a get method to get around the issue we had earlier. Public t get int index, and okay, it already suggested the code. I blue bastard. Anyway, return array index, and we can now make a for. That actually means we have to do something else too. Equals 0. I less than infos dot. We don't have a length yet, so let's do that. Let's do it in the same style we have with arrays. Make a property for that. Public int length. We're only making a get. Return count. So we can do it like this. Plus I, and then infos.get I keychar. Let's run the code. B, C, D, escape, CD. Now this might be a good option, or a good point to show you something else cool you can do with the keyword this. We've seen a couple of uses so far. It's rather versatile for something that's seemingly useless when you see it the first time, at least if you follow the order of learning stuff that I used here. We can create a very special method using this. Public t this int index. Actually, let's use also a new. Okay, no, let's use the classic one. Get return array index. So what we have here is a very special property. As you can see, it looks basically the same as this one above, except we use the keyword this and these square brackets. This is a special type of property that lets us actually pass in arguments as if it was called like a method. So instead of get and then passing the I as an argument to the method, we can use just square brackets directly. So we still pass in the argument I. So now this code looks just like the array did. Very special property. And you're not limited to just the integer. You can do other stuff too. You could have a string and maybe params, and I'll use whatever. You could have full rain here. You can treat it like a method, actually, like a normal method. Weirdly looking method, but a method nonetheless. And you just pass on the arguments then in here as if it was a method call, which it is. Just a special looking one. Just keyword this, and then the different arguments and square brackets instead of round ones, normal ones. And the rest is just a normal property where you get to use those arguments just like in a method. So we can use length and the index just like with an array. Makes it very convenient to use, to read the data. But we can also just add data to the array without worrying about the total size. And we can also replace the set. Can use it index. Let's do like that. This will call the insert for the set part, because this property, this special property, isn't only for reading, it can also be used for writing. And we're just gonna call the insert method again, because I want to have the same code add values in every single circumstance. Because it will make things easier potentially in the future. If we know that every single value that is added has to pass through this line. That's just very convenient. For the same reason, we should also do it like this. Consistency, so every single code that reads a value has to go through here. Alright, so instead of info add, we could also do like this. Like an array. We could basically treat this like an array, except we're not on a fixed size. We can actually increase the total size. And this is the basics for a dynamic array. And these exist in basically all languages. And there are a couple variations of that. The most simple one you can find in C# that I'm actually going to use now is called list. And as you can see, it's not part of the default namespace. It's another one we have to import, a rather lengthy one. But with this, we have almost the same structure as we used here, except it's not called length here, it's called count directly. So they rather go for count to return the count instead of length. So length is still used for arrays, but not for list. But other than that, we can use it just as is. 1, 2, 3, 4, 5. Enter. 1, 2, 3, 4, 5. That is list. It's also just dynamic array, basically. We have some additional features we can use, but as far as you are concerned right now, this is just a dynamic array that lets us do all the things we have done so far with our class dynamic array. Now, what I've mentioned, dynamic arrays come in different variations, different flavors, and they're meant to solve different problems. This one is the very basic one that's the same as list, which is just, I want to have a static block of memory that contains all my elements, and I can access all of them using a simple index directly, very efficient. But I also don't want to be boxed into a fixed size. I want to have more options to increase the size as the program runs. I want to be able to grow my array. And it does that wonderfully. You only have to pay attention to the growth rate, potentially. If you have a specific application where this causes issues, you might want to simply write your own version of that. If it's just a simple storage solution, then a dynamic array can be whipped up extremely quickly. And then you can define your own way to increase the size dynamically. Maybe you can actually use cues you get from your program to inform the dynamic array for how it should increase the size over time. Maybe it's not even always the same growth rate. Maybe you can adapt it as the program goes along and you have certain clues as to what's more probable to happen. Those things can be useful if you want to optimize your program a bit, but that's really in-depth optimization. That's probably not your bottleneck if your program runs slow or takes up too much memory. Just to mention it, that's where you might decide to write your own stuff instead of using the existing one that's pretty darn good. Like, personally, I've never had the situation I've never come across a situation where I had to write my own dynamic array to replace list because of optimization issues. That never happened. Performance was always way worse because of something else. Now let's talk about the other variations. If I'm not trying to replace an array that I can resize. There are two major types of dynamic arrays, though I'm stretching the definition maybe a bit here, that we need to talk about. They're very basic data structures in computing in general. Right now, I'm not really using all the features of this list. I'm just adding values as they come in to the end of the list, and then I'm just going to read them out from start to finish, and I'm done with it. The linked list, in my case, would have worked just fine, except for the memory. Well, I'm not going to say a performance issue, but except for the memory thing that I personally just don't like of the linked list, then it would have been a perfect solution. It had all the features I required. I don't use this list right now because I need to access individual indices at different times, or have to suddenly change specific values in the middle of my list, or add some in the middle of my list. What I actually use here is also called a queue. Queue. A queue is one of the two basic data structures that is simply intended for items go in and items are read out again. And the order in which I read items out of this data structure is the same order in which I feed them in. The term you're looking for here is first in, first out. So if I type in my keyboard 1, 2, 3, 4, and I read that data out, I want to also give me back the data in this order, 1, 2, 3, 4, to output it in the right way in the console. And in the queue, I do not care about any items in between. This order of items is very important to me, so I use a queue, because I do not have to access individual items in the middle of anywhere. I don't even have to start with the last item I added. I always only care about the first item that I've added, and then the one that I've added after that. And that makes a few things easier, but also more complicated. For using things, well, we don't really have the insert anymore, because we can't add specific items at specific positions anymore. We can just add items to our queue. Let's rename this. Just add items to the queue. And we can also not just get random elements back. Let's also remove the property here. We can only get the first item back that was added, while also removing it from the queue at the same time. So let me just make a quick list here. Would have been easier if I prepared the tablet now. Let's say I start with 1, 1, 2, 1, 2, 3. I just add more numbers to the queue, but then when I read them back out, I'm left with only the rest of the items. Make sense? So I start maybe with a 1, and I add a 2, then I have 1, 2, I add a 3, I have 1, 2, 3. But then I read or remove the first item, and I'm left with just 2, 3, and then I remove the second item, and I'm left with just a 3 in the queue. So let's first switch this out. This was array com plus plus. This value. Let's keep that logic first. And for here, we can start with a simple return array 0 to return the first element. Now the resize logic we can keep for now. We don't also keep that. Let's keep the count. We start with an empty array still. Yeah, okay. In the beginning, when I add items to my queue, it will behave exactly the same as my dynamic array, or as the default class list. I'm adding items, I'm starting at index 0 in my array, and as I add more items, I will have to sometimes resize my array, create a new array that's bigger, copy all the values over, and then continue. Until at some point I start to read values out. Because the moment I read out the item, I also remove it from the queue. Whereas the normal dynamic array, the normal list, will keep all the items in there and I have to specifically remove them. In the queue, they just stay. In the queue, they don't stay. Sorry, wrong way around. In the queue, I have to read the value and then delete it from the queue. And the next time I call get, I would actually read out array at index 1 and then index 2. So let's maybe add another one. Private int first item. We're gonna read out first item plus plus. So we do the counterpart to adding values with count. We're reading from first item. So every time we read an item out from the array, we just move ahead the index for reading by 1. And so the next time we read, we get the next item. We do not get the first item a second time. We get another one. So if I add 1, 2, 3, and then make get 3 times, I get first the 1, then the 2, and then the 3. That's all fine and good. But what happens when I reach the end of my array? Let's say I have filled out my array with... okay, let's say I have 8 spaces in total in my array. 8 items space in my array, length of 8. And I filled in 6 of those items with values. What happens when I reach the end of my array isn't even the question. What happens when I reach that 6th item? First item now points to the next item, to the 7th item, which doesn't exist. So that's something we have to think about. We can run out of items now because we remove them. And if an unexpected situation occurs, what's the first thing you should do? Properly log it, or throw an exception, maybe both. In our case, we would throw an exception. So what we could do is we just look at if first item is greater than count. We just throw new exception. Oh, queue has no more items. Right, so we have some insurance if we hit more items, or if we read more items than we've added, we get an exception. Okay, so let's assume I'm adding more items. Maybe I've read all 6 items now, and I don't try to get the 7th one. I only try to read the items 6 times. I still have my array with 8 free item spaces, and the first 6 are filled with actual items that I filled in, but that I've also read out already. So the first 6 spaces are used up by items I don't need anymore, and the last 2 spaces are free to be used for the next add. Now I'm adding 2 items and fill out the rest of the array. I could read them out again. Okay, that's fine now. But what do we do when we add a 9th item? The array has 8 spots in total. The first 6 are filled with items that we've already read and can be ignored. The last 2 are filled with actual items that haven't been read so far. Now when to add a 9th item? If we use our original logic, what we would have to do is resize the array, in our case doubling it up to a length of 16, and then add a 9th item in the next free spot. And we'd have to continue doing that for all eternity. That is extremely wasteful. Again, we have an array already with 6 items that are not going to be used anymore in the first 6 slots. Index 0 to 5 are unused, and with our logic, they're never going to be used by anyone ever again. You won't get to read them anymore because we don't have the index to that. Get won't let us read that item again. So why don't we reuse those free spots now, starting at index 0, to add items back again? So instead of just continuously growing the array, making it bigger and bigger and bigger and bigger, like we did before, we can make use of the fact that we actually remove items from the queue and get free spots back. We get space in our existing array that we can reuse. We don't need to resize the array and create new free spots in memory. We already have them. We just have to change the way we look in our array. We might still have to increase the size later on. But in that case right now, instead of increasing the size, we just have to loop back our count to 0 and start from the beginning again. So let's try to phrase it differently. Instead of a count representing the index in our array where we can plug the next item in, count represents just the actual number of items that we have that are still available for reading. And the actual position changes over time. So even though count might not change, the actual position we want to read in our array might change. Because as we read and add items, we're just constantly shifting around which items or which indices in our array are free and which are reserved. Let's forget the resize for now. Let's not focus on that. Let's assume that our array has a fixed size for now, and we want to add a new item. Well, first item already marks the spot where the very first item is stored, or at least the first item where we're gonna start reading, from where we start reading with our get method here. And we have a count that gets increased whenever we read a value, which hasn't been decreased so far. Should I probably do that here? And every time we read, we decrease the value again. So we know that we have first item. What the hell? You know, I turned on the lights because I want to see something, and now the lights are flickering. That's a good sign. That's a very good sign. Is the stream still? No, I still have network. PC didn't bother reacting. So I think electricity is fine. Is it just the lamp? Ominously flickering lights are a good sign, right? Good omen. The spirits are pleased with me right now, right? Okay, let's just continue. First item already conveniently marks the spot where we would continue reading, and count tells us how many items we have. So if we add them up, we know also where our array ends. And now we have to do a little trick. There's a certain operator we talked about a bit quite a while ago that is related to division. And remember, it was this percentage sign, and it was the modulo operator. Gives us the rest after division. So 10 divided by 3 would be 3 point something. And in computer land with integer logic, it would be just 3. Because 3 times 3 is the smallest we can get, up to 10. We just ignore the decimals. But that leaves us still with 1 that's not accounted for. 3 times 3 is only 9, and 10 is a bit bigger than 9, by 1 exactly. And so 10 divided by 3 would be 3, but 10 modulo 3 would be 1, because it's trying the division and then returns the rest, the remainder of the calculation. So if we do this and apply it to array.length, we get a value that will tell us... how do I explain that? I really should have put out the tablet. Basically lets us loop around. So if we have 8 items, and if we have an array that has a length of 8, so we have 8 spots in total. We have first item in position 4, and we have a count of 4. That would mean we have first item 4 plus count 4, 8, and 8 modulo 8 is 0, because you can just divide 8 by 8, and that's a clean full integer 1. There's no remainder, so position would be set to 0. And that would be the index of the first or next free item we can add stuff to. So, does that sort of make sense? The modulo operation lets us loop back to the beginning of the array. Instead of continuing to grow and grow and grow, we can just go back to the roots, we go back to the start, and fill items in there. So we go for position, we set it to value, And we still have to increase the count by 1. Actually, let's do it this way. Because we added a new item. But we didn't need to change the size of the array for that at all. And if first item is actually 0, because we just started filling up this queue, then position will just be count and it will behave just like before. And this logic down here can actually remain. We still get the position and first item, which will increase in size, and we also took care of removing the item with count decrement. Not very succinct, but actually it's succinct. It's not the prettiest way to do it, because it might be a bit harder to read, but it's easy enough, I think. It's still just 3 lines. That's fine. But this logic itself is now not quite sound anymore. Because first item is now an index in the array, but count is just an amount that has no relevance to the actual position in the array. So first item greater than count doesn't tell us much anymore. But we can make it simpler by just looking at, is count less than 1? I mean, count now represents just the total amount of items we have, regardless of where in the array everything is stored, so we can just look at count. Are there any elements left? If no, then there are no more elements. Throw an exception. And if count is at least 1, we know that first item will point to an actual valid item. So that works out. Now the resizing is still something we need to do, but let's ignore that for now. Just for a moment, we're just gonna start out with a new array. Let's make it size 8. And we're gonna have to change this code a bit. So well, that's a queue now. So we're adding items. And then we can change this code to while infos.count greater than 0. Get feature. We don't use the indices anymore, like before. We just have to get the item, and once we did that, it will ignore the position and move on to the next one in the array. It will basically remove it from the list. Technically, the data is still there. We haven't overwritten it yet, but as we have no way of accessing that data from the outside, it is as if it was removed, and that's good enough for us. So this will just remove the items from the list, and we just continue to do so as long as there are any items in that list. Or specifically our queue. Let's try that, see if it breaks. 1, 2, 3, 4, 5, 6, 7, 8. And escape. 3, 4, 5, 6, 7, 8. That worked. Let's try that again, but this time I'm gonna add more than 8 items. 1, 2, 3, 4, 5, 6, 7, 8, 9. Escape. Now we hit an issue. First item is 9. Oh. The same logic we used for adding values has to of course apply to getting the values as well. We use first item as a basis for looping around to find the next free position. First item for reading directly also has to loop around. So what we do here, actually, let's store that like this. Int position equals first item, like so. Position. So remember the current value of first item, and why is the... Sorry, console was still open in the background, didn't notice, my bad. And Now we have to increase first item, but with the logic of looping around. So we can still make first item plus 1, the increment we did before, but we also have to make the modulo operation based on the total length of the array. So in the beginning it will just straight up be 0, 1, 2, 3, 4, 5, 6, 7. But then when we hit the 8th item, it will actually loop back. Because once we are on the 8th item, index 7, we hit 7 plus 1 is 8, modulo 8 is 0. So the next time we go into this method, the item will be at 0. And next time we add, it will also start at 0. So let's try that one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9. Escape. Now we have that output. Let's try that one more time. Let me just add some more items, so maybe it's more obvious what happens. 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E. Escape. Now you can see it. We've overwritten the values in our array. I actually broke a bit more. What happened here? That was not tested, by the way. That's a general question. The overwriting was correct, but the doubling up was not expected. That's fine. Getting items. Is it correct? Why did it overwrite? Let's quickly do one more. 1, 2, 3, 4, 5, 6, 7, 8. Just make a breakpoint here. 9. So info so far contains array of 8. Count is 8. First item is 0. That's all still fine. Array contains 1 to 8. Yes. Now we hit the 9th. And now we add count 9. And was right, because I didn't add that logic yet. That's my bad. So, yeah, the resize. I should now talk about that. So that logic works. But as you can see, count can now be increased beyond the bound of the array. We can increase count to 9, although the array can only store 8 items. That should be an issue. What I still need to do here is check if count is greater or equal to array.length. It's coming back to that specific feature again. And if that's the case, then we do have to call resize. So if the count is already at the limit and we still try to add more, we have to make the array actually bigger, because if the count is bigger than the length, we know there are no more free items in our array. The actual index at which we start reading, first item, that might be any index, that might be any value from 0 to 7 in that case, but the total amount of items is still 8. It's just not starting at index 0 anymore. We filled out all spots, however. So we still need to create a new array, and I'm just going to keep the logic with doubling it up. What I cannot do, however, is this operation here. I mean, I can do that, but it's not true anymore. because my operations have moved the position of the first item around. That could mean that if we just look at... Let's do just these two. If I edit this in order, let's say I have 1 there, 2, 3, 4. Let's say this is the state of the array. And the numbers represent the actual order of items in which I added them. So the 1 is actually at index 2 here, the 2, the second item is index 3, and then the third item is index 0 in the front. If I increase the size of this array, let's do like this, and well, actually it will have default values, just use zeros. It will copy the data over like this. And at first you might think, well, that's fine. I mean, the data is in here in the same order, so it should still work just fine in the new array, right? It's still the same order, we didn't change anything. That's the issue. This is the first item it will read. And this is the second item the computer will read. Because the computer knows there are more items, we have a count of 4, it will also read the item that comes after 2. But the item that comes after 2 depends on the size of the array. In our old array, the next item would be index 0. That's where we stored it. But in the new array, the next item would be here, index 4. That's not where we stored it though. This is a new array. So when we read the item, the logic will assume it's stored here. But the old item that stored it will have put it here. We have to move the data around to make the logic still work out. So we could do one of two things. We could leave this all at zeros and put the items in here. So we still have the logic. After the 2, we wrap around and go back to 0, where the next item is stored. That works out. Or we use this as an opportunity to resort everything and start on the first item, or start in the first index with the first item and do it like that. Two options. Both are perfectly valid, and you can choose which one you prefer. But I'm just gonna reuse the logic we have up here to just iterate through the old array and copy the values into the new array in that order. So we have still integer I for the new array. So this part can stay as it is. This part has to change because we're not questioning array I anymore. We have to get a second, let's do like this. Int j equals first item. Wait, like this? Ah, sorry. Weird logic for the for loop. I'm gonna do j in here. That can stay, so just count on I. And j equals, we use the old logic here. J plus 1 mod array.length. So the same logic we have up here that we use for reading is applied here for our variable j, which emulates how the system would have read through the old array. So j goes step by step through the old array, so to speak, all the while I will go through the new array step by step. And j can start at any position in the old array and the logic will still make it work. And I will just start at 0. So let's try to see that in action. 1, 2, 3, 4, 5, 6, 7, 8. Let's make some breakpoints here. Emitting 9. So after adding 8 items, we have a count of 8. All item positions are filled from 1 to 8. Now we're adding the next item. I'm stepping in now so we can see everything happening. Count is now 8, which is the length of the array, so we have to resize. So we create a new array, which now has 16 elements. First item is still 0, so right now, since this is the first time we loop around, the order is actually correct. So these comments do not really matter. I is 0 and j will be 0, and it will just copy the array 1 to 1. So if I just go to here, new array will have 16 items, but still from 1 to 8. And then the rest is just zeros. And let's put escape in here. So that logic still works. It copies over the array data, that's fine. Now after we've done this, let's try to add more items. I'm just copying the loop, so remove the items here, but only 4. Let's do it like this. So we add items into the queue, and then we read only the first 4 items, and then we're adding more items into the list. And then we put out all the rest that is in there. 1, 2, 3, 4, 5, 6, 7, 8. Escape. Like that. And now I'm doing A. And this is the current state of the array internally. We have 4 items left. The array itself still has 1 to 8, but our first item has moved to spot 4. Index 4, because we already read the first 4 items. 1 to 4. So when I add the next item now... hit the wrong key. My bad. Sorry. Let's just start this again. 1, 2, 3, 4, 5, 6, 7, 8. Escape. Let's make another breakpoint. It's already there. A. That. Step into. Count is fine this time. We have filled the array still with the values from 1 to 4 in the first 4 indices, but they're not used. Count tells us that we have the open space. So now, when we calculate the position, it will actually wrap around to position 0 and set the value in there. For some reason it jumped ahead. Don't quite know why. Damn, let's continue. B. Key pressed. Just fills the value in. I'm just gonna B, C, D, E, F, G, H. This time it should actually have increased the size. Escape. And that means if we look at the array, start at index 0, we will start actually at 5. Previously that was the 1, but we overwrote this with a 5. 6, 7, or actually we didn't overwrite it, we increased the size of the array and the new values were sorted in there. But yeah. Let's clear that up. And let's start that at 0 again, use the old logic. If no one uses the array or the count at the queue, then we're just gonna leave it as this grid. And that's the queue. We add items in and we get items out. And as long as there are items in there, it works. If we read more items than were added, we get an exception, because every time we read an item, we remove it from the queue. That's one of the 2 other structures we need to look at. And let's talk about the third one. Queue was a list where we want to get the items out of the object in the same way we put them in. So if I put in 1, 2, 3, I want to get out 1, 2, 3. There's another data structure that's the exact opposite of that. If we put in 1, 2, 3, what we're going to get out is 3, 2, 1. We want to get it in reverse order. And that is the stack. A term which you've heard a couple of times by now. And the stack is below. First in, last out. So I guess you could also say last in, first out. So Lofi, below, Lofi. Honestly, I'm not sure who determined which is the shortcut that you should use. I learned them as FIFO and LIFO, I think. Doesn't matter. Everything you put in gets put out in the same order, and stack is everything you put in gets put out in the reverse order. So let's rename this to stack and change it so it follows the new logic. Actually, no, let's not rename it, let's create a new class. Just copy this, just want to keep the old one. This is stack. So just rename that. And stack will have similar logic. As soon as we remove an object, as soon as we read the object, we remove it from the list, and then we can add an object again. However, stack has an advantage. Because we only remove the last object, the items that we add to the stack can remain at their position until they're used up, and then immediately be used again without moving any indices around. What I mean is, with the queue, we move the position, we move this first index around all the time. First index was the item we need to read, and we adjusted this first item every time we removed, quote unquote, removed an item from our array to account for removed items. So next time we try to get an item, it will be the next in order. And the order in which we added items was following the same direction, so to speak. So my viewpoint for arrays is that the index on the left is index 0, and the further you go to the right, the higher the index. That's how I view arrays. And for the queue, we would add items by going further to the right, and we would also read items by going to the right. And in the end, we might wrap around to the very beginning on the left, but then still slowly walk to the right. For the stack, however, we add item while walking to the right, increasing the size if necessary, but when we read them, we go to the left. So the positions are constantly reset, so to speak. I don't have to keep total track of how far am I in the array, when do I need to wrap around, where are the items currently positioning, how is everything shifted. I'm gonna keep the count, because that's still useful, but we're gonna remove the first item. We don't need that anymore. Resize, we have to adjust, of course. Position is just gonna be ++. Just like before, because we add new items at a fixed position. We already know ahead of time where the position will be every single time. If you have exactly 5 items, then the next item you add will be at index 5. Always. It will never be a different position. Because every time we remove an item, we will just go to the item before that, to the left. That's the previous one, the one we added before that. And when we add a new item after that, it will just be added on the right. So, I'm not sure if my mental image makes sense, but because we do not add while walking to the right and read while walking to the right. Instead, we walk to the right and to add and remove by walking to the left. The position of our items, the current items we're interested in, that position shifts around while still aligning with the actual index position. That doesn't make sense if I say it all. This would be so easy to draw. Okay, next time I'm definitely putting on the tablet again. This is definitely a sign I should not try to explain things. Visuals are always better. So let's put this back. Can still do count less than 1. We get an exception, just this time for the stack. And return the item at count. And be done with it. So I guess we could also do that down here. Makes it a bit more consistent maybe. Looks more correct to do it this way. So access the array with a decrement or increment. More consistency here. And because the array positions do not change, like if it's the old array or the new array, we always start at index 0 and go to the right. We can just stay at index I all the time. We don't have to use a J to have a parallel walk. Increase all the rest, and that should be it. If I just switch to stack now. Yep, that's the wrong one. I want the dynamic array one, yes. If I do this now, it should, in theory, just work. So 1, 2, 3, 4, 5. Escape. 4, 3, 2. And didn't put out the 1. Still that same issue I had before. I do not know why. And it must be so obvious. It must be so bloody obvious, and I cannot see it. But as you can see, it reversed the order. Let's try that a bit more. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V. So, reverse order. Still messing up something somewhere. But that is the stack, the other option. And as you've seen earlier, we have Q in the generics. Oops. So Q is a standard type we can use. Let's remove that here. We've already imported the list earlier. And right, because we have... Actually, let's use that as a chance to talk about that as well. We've imported, or we're using system.collections.generics. So in that scenario, we can ignore this part here. Well, we can ignore that part anyway. And it will just use Q. That's the point of using. In my case, however, this has a conflict because I have Q, the class Q, in my own code here, as well as in the using. And if I just say Q, it will assume I mean my own class Q that I have internally here, in my own namespace. So if I want to use the other one, I have to fully write out the namespace as well. Or I could go back and put that in using as well. Not sure if I talked about that yet. But actually, I'm not sure how that works with generics in the using. I thought it was just this. Yeah, it was this, okay. So now this is still wrong? Because it's not referring to that one. How do I... Honestly, I'm not sure how to use that now. Usually in a class you would use that logic, you would use using some name equals full name. And then whenever you use it in your code, in that same file, it will automatically know, oh, you meant this specific using. And otherwise I have to specify it. But it's still in here, like that. I do not know how that works with generics though, admittedly. I've never had that before. I'm gonna look that up. That's interesting. Never thought about that. Cool. Anyway. So yeah, queue and stack are both standard types, just as list was. Because they are very common data types. Very common data structures. And they all fundamentally work based on the principle of I have an array, and if my array isn't big enough, I create a new array, copy all my data over, and then use that new array. And as far as I know, they all use the basic logic of every time my array is too small, I just double it up. So those are the three most common flavors of dynamic array, at least as far as I know, in C#. And they are fundamentally rather simple, despite how many issues I had setting them up properly. So maybe take that as your lesson. Do not try to implement them yourself if you don't know for sure that you need them. And even if you know for sure that you need them, you probably don't. Just use what's already given to you in these standard namespaces. It will work well enough for almost every scenario you will have. And yeah, that's it for me. I'm just gonna leave them. As your homework, maybe two things. One, try to recreate each type on your own, each one once. If you want to be very creative, you could also try to use the dynamic array we built, the list, so to speak, and use that as a basis for your stack and your queue, instead of making the same logic 3 times. That has some advantages, maybe, but also some disadvantages. Yeah, try each of these data types, just a list, dynamic array, just an array that internally can expand when needed, a queue, you can add items and you can remove items, and the items come out in the same order you put them in, and a stack, where you can only add items and remove items, and the items get removed in the reverse order in which you add them. And also, just as an exercise, try to implement this program, this logic. I'm pressing keys in the console and I have them output using a linked list. Just to try that again. You saw an example of the logic earlier. It wasn't very refined and I didn't really have a good output for that. And that's gonna be my homework, figuring out what the hell I missed here. And why the lamp is blinking. Flickering lights. Yay. Right. See you next time.